People looking at the night sky in ancient times asked questions similar to those we ask today. Is the universe infinite? Where we came from? Where are we going? Many of these questions remain unanswered. It was said that these people abstracted too much without being able to prove their thesis. They were the philosophers of those times. When Galileo perfected the telescope and detected Jupiter's 4 main moons, a slow process of distancing science and philosophy began. Measuring instruments were gradually evolving until the scholars of our times opted for the thesis that there's only what can be measured directly. Lord Kelvin, English physicist, 1824 to 1907, made this very clear. I have often said that when you can measure what you are talking about and express that measure in numbers, you know something about it. But when it cannot be expressed in numbers, knowledge is limited and unsatisfactory. It may be the beginning of knowledge, but thought will have barely advanced to the scientific stage, whatever the subject. When Heisenberg, a few years after Lord Kelvin's death, postulated his uncertainty principle, this stronghold of physics was shaken to its foundations. Halliday and Resnick, in the book Physics 4, on page 310, tell us. Some physicists believe that only measurable quantities have real meaning in physics. Only if one were able to focus a super microscope on an electron in an atom and one could see it circling its orbit, would it be fair to say that the latter had meaning. However, it will now be shown that it is fundamentally impossible to make an observation of this kind, even with any ideal instruments conceivable. As a result, it is said that these orbits have no physical meaning. The Images from the Universe project tries to draw the viewer's attention to the importance of our points of view as isolated observers that we are. When we try to understand the universe, our brain is unable to directly perceive and measure much of what goes on around us. The uncertainty principle is related to our sensory limitations. Furthermore, all the methods we develop to assess or measure events in the visible universe are appendages to our memory. For its part, the universe doesn't care what we think about it. It is possible to enumerate some things that would be outside the visible universe. Among them, energy and dark matter, black holes, the future light cone of events, and time itself, which might exist inside these virtual cones. Despite these limitations, philosophers of our day could not give up science. Because, thanks to it, we now have enough scientific data to allow us to make responsible abstractions about the nature of the universe. This did not happen in antiquity. I don't see why philosophy should be separated from science, because one depends on the other. Einstein never set foot in outer space, but, acting as a philosopher and scientist, he predicted that if he were in a vacuum, he would not be able to tell whether his body would be immobile or in a straight uniform motion. Einstein also abstracted that if he could move at the speed of light, he would not be able to tell if at some point he would be on the crest of a light wave or in its valley, as he would be synchronized with light. For the brain of the great thinker, there would be no oscillations in the movement of light. Light is the cornerstone for us to establish our points of view. It's what allows us to look at the night sky and see the distant stars, which is always late. Acting as a messenger, light would make space itself a phantom or fictitious entity. That is, space would not have the power to communicate any events directly to us, whether at the level of atoms or on the astronomical scale. For that, it needs light and time. In fact, our brain needs the help of both. The vacuum appears to be a completely empty and dark place, in the space between the stars. However, the light is there, even though it cannot manifest. When light and cosmic radiation manifest to us, we already find ourselves looking into our own past. That is, our memory, sustained by these electric fields of radiation, places us in a kind of temporal exile, in relation to the true universe. In a place where particles cannot be directly apprehended. The virtual separation between light and space would be a consequence of the packaging of light in the form of the photon. You don't see an electron directly until the quantum of light hits it and spreads out in the form of a photon. The particle is, then, called a photoelectron. One of the peculiarities of quantizing light in the form of a photon is that it does not require measurable time. After the collision between the two, the photon and the electron appear simultaneously, merging into one thing. Therefore, in practice, we cannot separate light and space. This would lead to misinterpretations, as would be the case of thinking that light waves would be continuous before their scattering. Even without being able to measure any time interval between the quantum's collision with the electron and the photon scattering, the quantum system operator has the vivid impression that the particle is sighted late and, therefore, out of its true position. Only our brain would be able to perceive and translate this subliminal information in the form of a spatial displacement of the particle. No experimental method would be able to do this. This illusion of particle displacement would be created by our memory's dependence on time. For a particle to move into motion, its position must be registered in more than one time, according to the concept of instantaneous velocity. Let's see what Alan Tapler tells us in his book Physics for Scientists and Engineers. At first sight, defining the instantaneous velocity of a particle at a given instant seems impossible. At any given time, a particle is located at a specific point. If it's positioned at one point, how could it move? If it is not moving, how could it have speed? This paradox is resolved if we remember that, in order to observe and define a movement, it is necessary to look at the object's position for more than one time. Therefore, even though that quantization of light is a timeless process, in which real particles would be virtually immobile, when it comes to our senses, the scattered photon would also act as if it were a unit of time. Time is intrinsically linked to the curvature of space. A flat space could not hold time. Therefore, quantization could be simulating the curvature of space itself, something that, according to physics, does not exist, because it cannot be measured directly. Space bends because light bends, not the other way around. Since quantization would be a timeless process, this curvature of space would be fictitious or illusory, at least until the moment when light hits the electron and spreads out. This could be extended to planetary orbits, as the retrogression of Mars could not be assessed without the aid of sunlight, which the planet reflects back into space. Kepler postulated that the actual orbits of the planets had to be elliptical, and not circular, as was thought at the time. However, circular motion took on the appearance of physical reality, keeping humanity under its yoke for centuries. When we look at the diagrams in the geography atlases, the impression we get is that all 8 planets would be arranged practically on a same spatial plane, in relation to the Sun, with small deviations. There is a virtual arc in the night sky running in an east-west direction, where the planets are more or less aligned. It's no use looking for planets much further south or north of this imaginary line, because they won't be there. Considering that the quantization, or packaging of light, was influencing our views due to the apparent fusion between light and space, promoted by the retention of time, let us analyze some theoretical developments. When we retrace Earth's motion to the Sun, in apparent motion over the ecliptic, it suggests that our planet's orbit would be circular, and not elliptical. This is because the image of the Sun, not the Sun itself, moves, during the day, from east to west with constant speed and acceleration, characteristic of circular motion. Despite the appearance of physical reality, this circular movement is illusory, and is certainly due to the behavior of the space messenger, and not to space itself. With this, outside of what could be directly measured, this light would be virtually nullifying the curvature of space, thanks to the retention of time. It sounds confusing, but let's try to visualize it in the diagrams. The Sun's future cone of light, which would hold light for 8 minutes in our future, fits the description of a straight cone. As it would result from the rotation of a right triangle, on its larger side, its base would be formed by a perfect circle. This is what we see projected into the daytime sky when it comes to the Sun moving over the ecliptic. If you drew a diagonal line through this straight cone, you would get an ellipse, where the Sun would always remain on one of the foci, or on the line that would join the vertex to the base of the cone. This real inclination of space is what would be behind the orbits of the planets, but which would be hidden from us by the light emitted by the Sun. Somehow, the process of packing light would act like a gravitational lens, showing us the Sun outside its true position. It comes to us late, and looking like it did 8 minutes ago. As the formation of the photon does not require measurable time, the illusion of continuous and relative movement in our past is created. That is, according to Typeter, to measure the motion of our star, we would need to know the position it would occupy in more than one time. This seems to put the 0 point of time definitively in our position due to the timelessness of the photon formation process. If you were to move through space, you would take this landmark in tow, always keeping you in the present. Everything around you would be seen as it looked like in the past. Another curiosity is that the 0 point of time could not be moved from our position to that of a distant star, except in theory. Measuring the position of the Sun through the speed of light is an indirect process of evaluation, or it would result from the extrapolation of theoretical concepts elaborated after the Sun's light scattering along with us.